Today we are going to look at spin-spin splitting in high resolution NMR. This is a low resolution NMR spectra of ethanol. Ethanol has three different hydrogen environments, so you see three peaks and the peak at 0 ppm for the TMS, which is your standard. What to consider on an NMR. In low resolution NMR, you see the different peaks representing the different hydrogen environments. You see the peaks at different parts per million, which is the chemical shift, which tells you the different type of proton environments you have. And then you can see the integration, which tells you how many hydrogens you have in that environment. We are now going to look at high resolution NMR, and that is where we see splitting within the peaks. This is a high resolution NMR spectra of ethanol. You can still see three peaks from the three different hydrogen environments in ethanol, but if you look at the peak on the left hand side, you can see it is now split into four. It is what we call a quartet. If we look at the peak at 1, you can see it is split into 3, and we call that a triplet. The peak at about 2.5 is the peak for the OH, and OH peaks are not split. If we look at the peak on the left, we know that that is from the hydrogens on the CH2, but it is being split into 4. So what is going on? The spin-spin splitting pattern is caused by the hydrogen atoms bonded to adjacent carbon atoms. And to work out the splitting, we use the N+1 rule. Low resolution NMR gives one peak for each environmentally different group of hydrogens, but high resolution NMR gives more complex signals, such as doublets and triplets. The signal produced indicates a number of protons on an adjacent carbon atom. And the number of peaks is represented by the number of hydrogens plus 1. So if you have a neighbouring carbon with no hydrogens, the peak will appear as a singlet. If you have a neighbouring carbon with 1 hydrogen, it will be a doublet. If you have a neighbouring carbon with 2 hydrogens, it will appear as a triplet. We use Pascal's triangle to help us understand the heights of the peaks. If you have a doublet, each peak will be the same height, so it's 1 to 1. If you have a triplet, if you look at the third line of Pascal's triangle, the height of the peaks will be 1 to 2 to 1. Here are some of the spin-spin splitting patterns you will meet. A singlet, a doublet, a triplet and a quartet. If you look at the heights of the peaks, you can see that they are linked to Pascal's triangle. Here are some more complex spin-spin splitting patterns. If we go back now to our ethanol NMR, we can start to understand the splitting a bit more. If we look at our CH2 hydrogens, they are beside a carbon with 3 hydrogens. 3 plus 1 is 4, so that is why the CH2 hydrogens appear as a quartet. If we look at the CH3 hydrogens, they are beside a carbon with 2 hydrogens, so N+1 means they appear as a triplet. A triplet quartet is a very common splitting pattern, and you will see this for ethyl groups on molecules on NMR. Here are some more common splitting patterns. If we look at the first NMR, you can see you've got a quartet and a doublet. That usually links to a CH3 and a CH attached in a molecule. Another common splitting pattern is a triplet-triplet. This would be seen if you had 2 CH2s beside each other but attached to different atoms. So for example, on one end you might have an OH and on the other end you would have a Br. The hydrogens then are not chemically equivalent, so you will get 2 peaks, and because each is beside a carbon with 2 hydrogens, they will appear as a triplet. Aromatic compounds, the hydrogens appear around about between 7 and 8 ppm, and unless we are using really high resolution NMR, they will appear as a singlet.